Hello and welcome to the 8th Long Products webinar. I'm Ken Landau. I'm a staff engineer here at AIST. And this webinar is titled AI Benefits Combining Process Control Data with High Performance Hot Temperature Rod Surface Defect Detection Technologies for Bar and Rod Mill Products. And sorry, let me get back in this. And with all our AIST events, we have an antitrust compliance. Do not discuss with others yours or your competitors' pricing procedures, or anything that may affect pricing, such as costs, discounts, terms of sale, profit margins, or anticipated wage rates. Do not make any statements about your own pricing or those of your competitors, and do not talk about what individual companies plan to do in particular markets or with particular customers. We also have an anti-harassment policy. Please read that over. Basically, be nice to each other. It's difficult to, with everybody being muted, it's difficult to not be nice. Here we go. Things to know. The attendee audio has been disabled. Questions for the presenter should be done through the question and answer feature that is on the bottom of your page. So if you hover your mouse towards the bottom, you should see the Q&A feature there. The host and moderator will determine which questions are presented. And this session is being recorded and will be available on demand replay at AIST's website. If you're having any technical difficulties, there's a email address, training@aist.org. We ask that no photos or recordings of this presentation be done, please. And let me introduce our moderator, Joe Kennedy. Joe is a professional engineer with Quad Training, where he specializes in steel mill operator training, site assistance, and operations planning. Joe has spent his entire 42-year career in the steel industry, working at over 90% of the North American steel mini mills. Joe is currently serving as the Roundup Chair on the Long Products Technology Committee. And with that, I'll leave Joe to introduce our presenter.
Okay, good morning. I would like to introduce today's presenter. This is Bruno Cettilangli, who received a master's degree in physics and chemistry and a doctorate in electrochemistry and corrosion. He is the director of Steel Process Product Development Consulting at SPPD Consulting. He's worked as director of process product development at Celsa Group in Spain and at GSI Group in the US as the director of process quality, and also as a non-destructive testing engineer at ArcelorMittal in Montville, France, and as a research engineer and engineer foundry at the Picini aluminum complex, also in France. Okay, Bruno, you may start.
Okay. Everybody has a first picture, so I will start. First of all, good morning from Normandy, France, for everybody. Hope you are in a good shape, and thank you and welcome to this long product seminar. So restarting, in fact, here my presentation will have a title of Artificial Intelligence. Excuse me, I'm just boring this kind of thing. Artificial intelligence benefits combining process control data with high performances, hot temperature, rod surface defect detection technology for bar and rod mill products. An industrial example would be presented. So going to the next slide, that's my plan in the presentation. First of all, would be speaking on the big process data. The second step would be with the high performances of a hot temperature rod surface defect detection technology for bar and rod mill products with 4 type of example: billet cracks, rhomboidity, groove cracks, other type of application, and finally the conclusion. So let's start with the first item, which is a big data. So the big data, in fact, what we are talking about, the process control data, are the zillion of data we are using every day or every month, feeding PLC level 1, level 2, level 3 process control for automatic and manual adjustment in order to save safety, cost, and quality process consistency. This kind of thing is coming from the melting furnace to the ladle furnace, to the caster, to the rod mill. Because in fact here, we are dealing with the fluid information for flow pressure, weight for alloys, flux, carbon, scraps, any kind of addition, energy consumption from the input of electric arc, electric engines, geometry with the size, length, diagonal, temperature with the water, liquid, solid steel, and chemical analysis on gas, water, slag, steel, motion with the speed, the oscillation, the vibration, electromagnetic steering, and sensors like infrared temperature and electromagnetic signal, etc., etc. So we need, in fact, to fill the bag of this guy here, and we will have inside all the process information through the analogical signal and for the use of a PID specific items to deal with the process we were talking before. So from there, we have a big challenge, because we know that on one side, we have this guy waiting probably for some kind of explanation on hot surface defect detection occurrences. And on the other side, we have the big bag of the process data waiting from the steelmaking area and from the rod mill area. So in between, we need to organize a highway continuous data exchange just to be able to synchronize as best as possible the information from the surface defects, which are normally, I would say, 80% of the claims in the steel in comparison with what we could get from the process data to be able to improve the process. So from there, I would like to do some kind of a reminder specifically on the Eeddy Current system with a 3H, because in my presentation, I need to have this information available for you. So the 3H evolution of the Eeddy Current are first the one from the 30, 40 years ago, with the basic coils for the Eeddy Current with some kind of a medium frequency, with the analogical signal printed on a printer here, and with some kind of information just trying to say the coil is good with a green light, the coil is bad with a red light, and that's about it, with a lot of suspicious condition on sometime the way the Eeddy Current system was working from the operator's point of view. Now, in fact, we are in a situation where we are able to work with robust equipment, working at hot temperature with a very high frequency. When I say very high frequency, that's more than 100,000 hertz for this kind of equipment. So we have a better sampling. We have a mapping, like this one will be going through after that. And we have the quality index. And just to point out this kind of thing here, I have some information just showing how it's working. So let's say that we have, of course, the analogical signal. We will have a threshold. We have several thresholds available. And we have the mapping. So what's the mapping? The mapping is the complete picture of the coil with the information of what kind of number of defects that I have, and what would be the critical defects where they are. So let's say that the square is a 5.5 kilo, which is almost 10 rings on a 5.5 millimeter. The blue color is just saying that there is no defect there. When we have a slight color like yellow or green, we have some kind of slight defects. And when we have a black square, that means that we had big defects or critical defects there. So that would be better just to take this information seriously. In this kind of thing, the quality index, let's say to make everything simple, just saying, okay, the number of a black box are the quality index number. So if you have a 15 black box, that's the quality index is 15. So that's how it works for the Eeddy Current system today without any kind of other system. So we are able to detect the short defects, and we are able to detect some kind of long defects, sometimes like overlaps. Okay. Now, excuse me, I'm just trying to, I could not. So, looking at the next step in here, I'm just showing what is the step today with the combination of the Eeddy Current and the vision. What we are talking is the ADI's equipment from his end, and this kind of thing is synchronized in between Eeddy Current and visions, which means that not only we have the quality index, which is registered with an Excel chart by coil number, heat number, billet number from the casting area. We have also the mapping, as we were talking before. But in addition with that, when we have a critical defects coming with a black square, we have automatically a picture coming with this kind of defects. In addition with that, for the long defects, we have a specific scanning along the coil just to catch the long defects which are possible on the rolling side. So let's go to the next slide. The next slide just showing you the same thing in here, quality index, mapping, pictures when I have some kind of a black square opening. And here we are with all the defects we are able to classify with the algorithm of the equipment, which means that we have here, excuse me. We have here, yes, we have here billet corner cracks, typical defects in here. We have the scab from a product which are rolling object, overfill, overlaps, crack rolls. In addition with that, hair from guys which are just scrubbing, crushed overfill, overlaps, and scab with a neck down. So if I'm working with this kind of thing, I would say I am almost ready to fill the bag of this guy, just saying, okay, now I have a defect with the quality index, which is over the standard. I have a number of black square with the pictures which are describing what I have. I am filling my coil with this kind of information. So that's how it's working. Now, let's go to the organization of all these kind of results from the ADI information. When we are working like a standard linear approach and action, the information from the ADI is coming through, of course, the first a quick check from the rolling mill people who are along the rolling mill with finishing, no twist mill, reduction size mill, roughly mill, intermediate mill, everything like that. And they try to recognize what kind of defects is there in addition with the picture they just received from the vision camera. In addition with that, of course, when everything is confirmed, we have to send the information to the coil yard to separate the coil which could be involved with some kind of problem. And after that, in fact, we are just going on with loading the heating furnace with billets, which are sometimes good, sometimes bad, but we do not have still the time to do something, really speaking. And after that, after the fact, that would be, in fact, after several hours, would be looking at what kind of a number of strand of strand with a bad defects we would be looking for. And finally, would be sending the information to the caster to try to say you have to correct some kind of problem if there is a problem from the casting area, of course. Now, if you are looking to this kind of standard linear approach and describing well, the thing which is described in this wheel is some kind of first of a Six Sigma approach with a control, define, measure, analysis, and improve steps, which mean that I divided into this wheel. On the right-hand side, you have now with the ADI's equipment, which is Eeddy Current plus vision, we have more or less than 30 minutes action when we discover the problem. In comparison to what we have before without the vision, I put this kind of information here. For example, on the main pulpit of the operators, in 5 minutes, they know that there is a defect with a picture. Before, without vision, you have to wait more or less more than 20 minutes. With the control operator and starting on the investigation on where are the coil, etc. Now we have a 10 minutes reaction. Before, without the vision, you have more than 2 hours. With a shift form and adjustment and everything organized, we have more or less a 30 minutes action plan on the right-hand side of this wheel. And without vision, that could have more than 12 hours reaction because, of course, people are not there and they are not doing the right step, probably. But anyway, that's 30 minutes action today with the ADI's equipment. I would say the Eeddy Current and the vision synchronized all together. Now, on this linear approach, of course, after that, you have to send the information to the process people from the steel making and the rolling mill. So they would be able to work on what was wrong on this kind of thing. You will send the information to the steel making and the rolling mill for the modification or the complete checking of the process. But that would be probably 12 hours or 24 hours after the fact. And finally, you have also the information for the rolling mill maintenance people and the steel making people on the electronic, mechanical things and computer things to organize. So that is what we call the linear approach. Now, I would like just to show you one example, the first one, in order to check everything. Again, I would like to recall this kind of graph again with the analogical signal here, the mapping, and let's look at this mapping here. Again, 1 square is a 5.5 kilo, which is 10 ring in 5.5 millimeter. When you have a dark spot or a dark square, That means they have a critical defects, and the addition of all the square are giving you the quality index. So when you have some time, you could rebuild the historical data on the rolling order of this kind of sequencing, which is, by the way, an 11 that's 11 hits sequence on 10 millimeters. So if you go through the rolling mill order, you find out that you had some kind of a big problem at the beginning. And recalling again the information, 1 point is a coil. The Y index is the quality index of the coil. The color is the heat. So we are with the first heat of the sequence in the rolling order, and we are with the last heat of the sequence on the rolling order too. So you get the impression that you are facing some problem at the beginning of the rolling. Now, if you go further and you reorganize everything from the rolling order to the casting order with the chronological heat number, you find out another kind of picture, which is more or less normal, because in fact, if you are depiling the billets, you have the reverse way here, which means that you have the last heat involved here on the sequence of the casting area. You get some bad heats involved with some kind of problem. Now, if I'm able to reorganize everything from the casting area, which means that reorganizing the quality index by strand number from the casting machine, I will be able to build this kind of graph, which is a strand 0, 1, 2, 3, 4, 5. The strand 0 is a mixed bag of billets coming from any kind of strand, because the identity was lost at the beginning. So just forget this one. But we have the strand number 1, the strand number 2, 3, 4, 5, and what we would be looking for is in fact a small problem on strand number 2 for 1 heat here, which is a very particular defects at one time in the process. And you have another one, which is a big one, which is the 4 heats, last heat of the sequence here, of the casting sequence, which are facing some kind of a big problem. Now, if I'm going to the good graphic software with the statistic information here, I'm able to rebuild the tendency for each strand. And you could see that the strand number 5 is worse, of course, and with an average number of quality index, which is high, and with a standard deviation, which is probably high. And you have this strand number 2 with a local problem on 1 heat. So doing that, I would like to pass to the next slide. Another thing, which is, of course, related with the P factor with the ANOVA system, just to reinforce what would be looking for. The strand 0 is 15% more or less of the quantity of billets rolled, but the other one, which were known with the strand number 1, 2, 3, 4, 5, are there. And you could just find out where are the guilty guy. The guilty guy, of course, what we were just saying before, that's strand number 5 with the quality index average, which is the highest of all together here, and the standard deviation too. And you have this kind of spot with the strand number 2. So I'm just saying that with all this information, you know what you have to kill, and you know where you have to go after that. In addition with that, from the pictures taken by the camera from the ADI's equipment, you know on time what kind of defects you have here. And thanks to the algorithm of classification of the equipment, you know that's a corner cracked billets involved with this kind of thing probably. And if you have the chance to look at this kind of thing, because you have some billets left, you have some, excuse me, I just push the wrong button here. If you have some billet left here on the billet yard, you could recognize that you have these kind of small cracks coming, which could be probably repaired with some kind of grinding machine. Now, if I'm going to the next slide, I would like to now go through the star system approach connection, which is different from the other one. You remember the other one, we were with a linear action. Here we are with a star action, which means that all these areas are connected immediately with the problem which is occurring at the rolling mill with the quality index and with the pictures of the defects and everything like that. So nothing is really changing on this side, on the right side of this wheel, because we have already beside the rod mill and beside the equipment all the information available. But in addition with that, I will distribute the information to the casting and rolling mill process people there immediately for the casting and rolling mill maintenance too, and production planning people. So they would be able to react on time. That's a key point in this kind of action. And if I'm doing that, that would be a different way to work, because the ADI equipment just giving the information that I found some billet cracks aspect problem. So the information is distributed to the rolling mill people, of course, to the quality department and the coil yard, to the entrance of the heating furnace, to the billet yard, and to the casting people too in the same time, which is important. So with this kind of thing, you could react very quickly on this kind of problem, because I will show you on this chart, on the Excel chart in here, coming from the casting area to the billet yard to the coil yard and the production planning with a final step with the customer. So if I am just on the linear approach, I'm not doing anything with the casting on time. I'm not doing anything with the billet yard on time. The only thing I know that I have 9 billets from 4 heats, which is 30 Higgs coil, to be scrapped, because we have this kind of corner billet cracks corner occurrence, which is at the end of the day 108 tons and not billed and not delivered. If I'm working with the star action, what I know, in fact, that's I already rolled 13 coils with this kind of problem of the strand number 5. So I know I have to replace this tonnage in here. And I have also 23 coils coming from the remaining lot in here. And I could ask the heating furnace at the entrance to divert the billets, the 23 billets at the entrance of the furnace, in order to send them to a grinding area to repair the billets and to save them. And I have also to ask the billet yard if they have 23 billets available somewhere on the same grade, just to keep the order at the same tonnage and having the tonnage ordered with the tonnage build, which means that we have to reprogram 36 billets at all. And the consequences of this kind of thing would be that we would be avoiding a scrap cost with the 23 coils or 3 ton, would be escaping the rolling cost too, would be avoiding also the fixed cost of the rolling, which is some kind of $38 ton. The additional benefit of this kind of thing, of course, we would be able, after rechecking with a casting area before all the production or before all the inventory, will be able to check with the casting area what they would be able to correct to ensure the consistency. So we are talking about machine learning here. We have also optimization of the billet stock inventory. We will have also the optimization of the coil inventory. And we have also the possibility to readjust the coil order. So quantity and quality would be safe and would be learning from this kind of incident. Consequence of that, the mixing of artificial intelligence and human intelligence make a good machine learning approach with the steel making and the rolling mill chain of production. Tonnage ordered and is a tonnage delivered and billed. Preventive maintenance preparation too. Improved, good vertical and transversal teamwork, production and product consistency, decrease emission due to the saving on the product which would not be scrapped, and optimizing, like we say already, billet and coil inventory. So that's where we are with the first example of this kind of things. Now, I have another example. The other example is this one with a rhomboidity problem with the strand number 3. So that's the guilty guy here. And we have all billets from strand number 3 with this kind of problem, which is producing on a box pass, these kind of big overlaps. And in fact, the warning of the ADI's equipment with the vision is just showing that we have a big overlaps occurring here when the coils are coming to the coil inventory. We could find out what kind of defects we have, which is the confirmation of the overlaps, but that's 1 hour after that. And in addition with that, of course, we have some kind of small disaster with a 1 hour down day for a spaghetti incident due to the bad billets with the rhomboidity problem. So going through this kind of details, let's go back to the information from the equipment coming, the equipment from the ADIs coming here. That's some kind of information of, in fact, standard coil here, which has no problem almost. The coil 22, but the coil 20, excuse me, the coil 22 here has a lot of black area, and they stopped to roll, and probably that was a spaghetti coil here we saw before. And here, that's another hit with a lot of black spot with some disturbing things because, of course, everything was wrong and perhaps we lost this coil. I could not say this kind of thing, but perhaps, fortunately, they were able to roll this coil, but it was not, it did not have any kind of incident with the spaghetti problem. But finally, the signature from this is the camera pictures from this kind of defect, which is an overlaps condition. And here, of course, everybody is able to recognize this kind of problem along the chain of production. So if I am going now to the star organization with this kind of thing, I got the information that I have a big overlap. The rolling mill people are looking around and find out that with the box pass, after the box pass, we have this kind of big overlaps condition we saw, and step by step, after 13 coil roll, we find out that the strand number 3 is the main guilty guy with the rhombo problem. So immediately we send the information, of course, to the rolling mill, but we send the information to the coil yard and the quality people just to start the separation of the coils on time in order to avoid some kind of pollution with the stock of this customer. In addition with that, we have the possibility to react on time to divert the billets of strand number 3 really at when we know the information. So we have to discard these billets, and in the same time we could start to make screening of all the stock on the billet from the heaths involved with the sequence and divert them. And in addition with that, if we are, by the way, doing some kind of specific production at the caster with the same grade or something like that, we'll be able to ask the casting to check everything from on the process to be sure that we are not repeating the problem for the next production. So if you go through the figure here, with a star connection with a strand number 3 rhomboidity problem, coming from the casting area to the billet yard, to the color yard, the production planning, and the customer side, we are here with 4 heats with a rhombo, which are producing 36 coils, excuse me, which are 4 heats multiplied by 9 billets for the strand number 3. So these coils will be scrapped probably. But I have also the remaining part of strand number 3 for the 6 heats coming from rolling, and that will be almost 60 billets coming. So that will be 60 coils at the end. So at the end of the day, you will have a 96 coil here, which is a 288 ton not built and probably scrapped. If I'm working with the star condition, which means that the equipment is giving the information at all the area here, I know that I have already rolled 13 coils, which would be scrapped. So I have to reprogram them with the PPNF people, production planning people. And in addition with that, I already rolled 23 billets, which would be discarded too, which would be, no, excuse me, 13 coils already rolled, but I could ask to divert the 23 next billet from the strand number 3, which are coming at the entrance of the heating furnace. So we'll be saving at least these 23 billets time for the rolling. In addition with that, I could manage with the 60 billets which are coming at the entrance of the heating furnace and not roll these bad billets in the same time. In the same time also, I would be also rechecking with the casting area what was wrong and what would be improved immediately, which means that at the end of this kind of thing, asking to the production planning department to replace the 36 billet from here plus 60 billets coming from here, I would be saving the tonnage to be delivered. And I will be also saving some cost with the rolling cost and the fixed cost for the 60 billet, and the rolling cost and the fixed cost, and probably the 1 hour downtime for a spaghetti problem from this strand number 3 problem. So finally, that should be some kind of $56 a ton saving here. And yes, here. And I will be able to do these kind of additional benefits, which are the machine learning and consistency at the caster, optimizing billet inventory with the billet yard, with the collar yard, readjusting order, and ensuring the quality and the quantity of the customer. So going to the next slide here, that's more or less the same kind of information I was talking before, mixing artificial intelligence and human intelligence will bring a good machine learning along the steel making and rolling mill chain of production. Of course, the tonnage order would be the tonnage delivered. If we have the possibility, we will have the preventive maintenance organized, good teamwork from vertical to transversal team, production consistency and product consistency. Of course, also decrease emission because we are saving energy for not rolling bad billets or bad production and optimizing billet and coil inventory. So that's the second example here. And I have a third one, which is with a star action on crack grooves. So here on the crack grooves, I will show you here what is a crack groove at the beginning of the crack groove problem. So here that's a slight mark, but which is already detrimental for the customer because that's a very periodic defect coming every time on the coil. And of course, the rolling mill would be able to check this kind of thing and would be looking at the inventory of the coils and organizing the coil separation on this part. And with only this kind of information, the rolling mill people could decide to stop the strand which is involved with this kind of problem. So the next slide is just going through the balance of this kind of thing. Excuse me, I'm just lost with the marker here because the marker make me some kind of thing bad. Okay. Okay, let's go again from this kind of thing. Okay, so now. Okay, so again, that's a groove crack from what we were talking about, the defects on the rod mill and the picture which is shown by the vision of the camera vision. Now that's what is appearing with the standard Eeddy Current system on 21 millimeter, for example, starting a crack groove here. So you need to have a 50 millivolt threshold just to catch this kind of thing at the beginning, which is not compatible with the background noise. And 35 minutes or 40 minutes after that, you get, of course, the big defects on the coil. But that's already too late because you already rolled a lot of billets there. So some kind of magnification here. Some kind of magnification here. That's the standard information from the Eeddy Current here. If I'm doing some magnification here, I could find out what kind of periodic defects I have. And there is some kind of signal here. And if I'm magnifying again, I have this kind of picture showing that there's a periodic defect and you have to be able to take care of this kind of thing. But that's with only the Eeddy Current. Of course, here, that's the next coil coming from the same strand. You get the same tendency. And when you change the pass and you don't have any kind of thing like we were looking before, and that's a translation of the absence of defect after the changing of the pass with the Eeddy Current system working. Now, the vision is able to tell you that you have a defect like a groove crack at the really beginning, and you could save time and money with this kind of information, which means that if I'm going back to the chart, the Excel chart I was showing you before, and we are dealing only with the coil yard and the billet yard in here, because that's only the rolling mill which is involved with the problem. remember that without the vision with the eddy current, probably would be spending 25 calls before stopping the strand involved. Here, with a traditional linear solving problem approach, there is still some kind of question there because people are not familiar with how to work with, and that's take time. And you have in few minutes you have 10 calls already rolled. If you are the star action and you know after the first picture or the second picture, you get this kind of groove cracks problem with a picture I showed you before, the people from the rolling mill could stop immediately the strand from involved with the crack grooves. And you have 2 coils to be checked and diverted probably, but you have 8 coils saved after that, which means that you save the rolling cost, the fixed cost, and the scraps cost on the rolling mill, which is some kind of $20,000 for all these kind of scrap, which was avoided by the rolling avoided of 8 coils. So I will ask to the production planning to reload 2 billets in order to comply with the order, which means that finally I will have again the order tonnage delivered and billed at the end of the month. So going to the next slide, again, same kind of process, mixing of artificial intelligence and human intelligence gives you the machine learning along the preventing maintenance, process consistency, product consistency, timely order delivered and billed at the end of the month, decrease emission with another green steel step production, and optimizing coal inventory. So that's the second example, and I will have, the third example. I will have the fourth one, which is in fact some kind of new things coming, which means that we are now working on the corrugated wire and mass control with the eddy current and the vision. And here, the ADI equipment just sending an information that I have some kind of outstanding condition on the shape of the groove, which are here. So of course, some kind of recognition on the rolling mill side and some kind of action for discarding the coils which would be probably impacted for this kind of problem. With a higher magnification or this kind of thing here, you could discover that, of course, there is some kind of problem in the shape of this kind of product. And you could also find out that you could measure the edge and the width of this kind of form to be sure that you are complying with the standard. So not only you could have some kind of measurement when you like to do that on time, but also you could really decide just to stop and to change the path when you like to do without risking any kind of big problem at the end with the customer. Another application of this kind of thing is a mass control. We saw that, of course, the mass control is also an application with the eddy current system. And here that's just some kind of application with a combined view of the intensity or the electric consumption of the electric consumption, electric consumption here on the reduction sizing mill on a 23 millimeter, the sizing gauge answer, the mass control answer with eddy current, and the density control with eddy current too, and the temperature here of the product exiting the rolling mill. So here you have, as usual, the increase of the amperage at the end of or at the tail of the coil, which could be correct or no, depending on what you could do. You have the comparison between the sizing gauge and the mass control here. And in fact, you could find one thing interesting here, that you have a gap in the middle of the coil here, which is more or less coinciding with some kind of drop of a consumption of electric power here on the reduction sizing mill, but we should also compare other information from the intermediate mill too. So that's another application to make all this information available from the equipment to the process people for the rolling mill. So as a conclusion, I would like to say that first of all, if we are able to organize a highway communication using the big bag from the process data with the big bag from the surface defect detection information, we'll be able to work as a 4.0 plant with the artificial intelligence and with the human intelligence, which will be bringing quick machine learning and training application, consistent algorithm classification exchange between production, process, production planning, quality, customer service, and shipping. Also, we will have a continuous permanent improvement methodology for production, quality consistency, energy emission, etc., etc. And I would like just to finish with this kind of thing. The surface defect detection problem is not only an investment for the quality insurance and the reduction sizing mill and the reduction mill, excuse me, but this is also a tool for the complete plant, which is from the melting to the final product. So finally, I would like to tell you that I hope I will not put you asleep. I will puzzle you enough, and I will wish you a good spring before your question. Thank you very much.
All right, thank you, Bruno. I have one first question is from John. And the question is, taking your example of rhomboidity on strand 3, isn't it probable that by the time the defect was discovered, the rest of the heat would have already been charged into the furnace, and therefore you would have had to have rolled or scrapped it?
Yes, you are right. But in fact, if you are able to discover at the beginning of the rolling of the sequence that everything is still coming from the strand number 3, I'll recall you that we have still 11 heats in the stock ready to roll from the same sequence. So you could act. Of course, you could not act at the beginning with the 36 billets coming, or you could act with one part of the 36 billet coming from the strand number 3. But after that, you have all the strand number 3 billets, which would be coming, and here you could organize something. That's what I mean, okay?
Okay. All right, and also the, I mean, when they come off the caster, only 1 in 5 is bad.
Yep.
So, there's a mix there, and they would just have to pull them out as they see it.
Yes, that's right. That's right.
Okay. And then I have another question here. It's about, is the hairline mark found on the billet during the the 12-meter billet cut into 4-meter lengths of a 150 by 150 millimeters, going to cause the surface defect, which would be a chip out or a lapping. So that's.
I don't exactly what you mean. In fact, you are saying that are we able to do the differences in between some kind of rolling object or some kind of problem from the casting area? That's what you mean? No?
Yeah, I'm not actually positive. This is a little choppy. So I know, Harash, if you would like to maybe clarify that question, that would be helpful.
Yes, I would say that, of course, if I'm going back to the picture here, let's say this one. This one here. So the hair and the scab, I would say, I'm not sure that's something, that's some kind of index of pollution of the rolling mill with something. You could have a product sticking to the surface. You could have some kind of product also coming from the billets, but depending on the size or this kind of thing, if that's coming from the billet, that would be a big piece of product here. But here and here, that's a small piece. I would be suspicious more some problem from the rolling mill, some guides which are with some kind of scrap inside and dropping this kind of thing sometime, and which is just some kind of thing you have to relate with. This one is really interesting because, of course, that's characteristic here, and you know that's a guide from the rolling mill. In here, perhaps you have some kind of problem from the billets too, which could be a lubrication problem with some kind of scab here. But of course, in between there and there, if I'm saying if I'm asking myself what the rolling mill people have to do, stop the rolling mill for this, for sure. Stop the rolling mill for this, I'm not sure. We have to look at what is the tendency with each strand of the rolling mill area and what is a tendency also with the casting area with each strand of the casting area. I'm not sure if I answer you correctly to your question.
Okay, right now those are the only 2 questions at this point. So if anyone has an additional question, if you could please send it over, I guess right away, and then we'll deal with it. So we'll just give you a moment in case there's any other questions.
Well, there don't seem to be any more questions. Bruno, thank you very much for the presentation. Joe, same for moderating. I'm going to take over the screen here for a second. And now set the our next event for the Long Products is the Long Products rolling training, which is May 11th through the 13th down in San Antonio, Texas. More details are on AIST.org. So with that, again, Bruno, thank you very much for presenting, and Joe for moderating this webinar. And with that, we'll conclude it.
Thank you.
Okay, thank you.
Have a good day.
Thank you.
Bye-bye.